those are kind of the fuller solvent. Aprotic means it's non-protic. Excellent reaction. If the starting material is stabilized by protic solvent, reaction rate decreases. This is the typical anionic charged the nucleophile. If it is stabilized by this kind of things, it's not good. That's why we use either DMF or DMS or any solvent. Okay, this is water. Why is that? Carbocation is stabilized by polar solvent. Among polar solvent, water is most polar solvent. Isotonic reaction has a transition state, and it doesn't have intermediate. And this isotonic reaction, second order reaction, bimolecular reaction 2, and retention minus inversion of the stoichiometry is not necessary. Okay, ethanol reaction has intermediate, carbocation intermediate, and SN2 reaction inversion. Ethanol reaction is not retention. If it is not retention, then what? Racemization. Generating mixture. Alcohol react with the chloride. It's not SN2 because carbon was not attacked. Oxygen attacked sulfur. This intermediate is formed. Next step, nucleophile will attack here and then release whole tosylate, including this oxygen. So this is activating of alcohol, hydroxyl group, and that forms intermediate, but it's a separable, not super reactive intermediate. Racemization is only SN1 reaction. There is no carbocation here. No racemization. Inversion not happened yet because this attack pyracemtide is here in the stomach. Oxygen attacks this center. That's why there's nothing happened. So there should be retention. To get inversion, you need to have SN2 reaction. SN2 reaction, carbon should be attacked. Okay? And racemization only SN1. Now you should have inversion. Okay? Now tosyl formed and then bromide come back and attack. can isolate this intermediate and then add the nucleophile. Nucleophile come here and attack with this SN2 reaction. That's why inversion happens. Difference between these two, PCl3, PBr3, PBr5, PCl5, everything similar mechanism. SOCl2 also same. Alcohol attack here first. It forms very reactive intermediate. Chloride comes back, attack behind. Product is alkyl chloride. In the case, alkyl chloride. SN2 happened at one time. That's why inversion happens. That's the difference between this class of reagent with the tosyl chloride. Tosyl chloride, the first attack, alcohol attack here, this is intermediate. This is kind of intermediate here, alcohol attack, this intermediate. But this is reactive, so chloride comes back and finish up that reaction. Then, this is intermediate, this is intermediate. But this one, SN2 happened one time. Carbon is attacked. This looks like one-step reaction, but actually two-step reactions. Attack here first, chloride comes back, and attack back. That's SN2. That's why inversion. Okay? To make sure, now if you do this reaction in two steps. Attack one time, inversion one time happened, Br minus attack again and release this. Product is RBr. Inversion and inversion. Then total result is retention. Okay. Racemization, you need to have carbocation intermediate. SN1 reaction. Okay. If your starting material is a chiral, that's an expensive pure material. You don't want to lose it by racemization. That's bad direction. Either retention or inversion, keep the chirality maybe good. Now, depending on your need, you can choose. Invert first and then do the reaction, then you get original configuration. If you want only one step, the inversion, then you choose tosyl chloride. Okay, that's the difference. Okay, PCl3, SOCl2, all the same. Alcohol attack and chloride comes back as an attack. SN2 happens first. Reactive intermediate is already inverted one time in this case. Tosyl chloride, no inversion. Then you do next step. Then you get retention product here, inversion product here. Okay. This may be most complicated, the part of SN2 reaction. But if you understand this, then you're okay for any kind of entrance exam or organic chemistry, sophomore level of understanding. If you understand it this much, you understand the stereochemistry. Living good ways, fluoride, chloride, bromide, iodide getting better and better, and iodide and tosylate was similar. Or tosylate is a little better. So tosylate is one of those best SN2 reaction in living good. That's why we went to tosylate as a good living good. Okay, interesting in SN1 reaction, water is the best living group. By removing water means with acid treatment, water is ready to leave, then water is removed, then carbocation is formed. Planar structure can be attacked in both sides, plasmization, SMR. Okay. I exactly said this. Tertiary alcohol with the acid, protonate, and then water is removed, and chloride comes back to attack SMR. Okay. May form E1, some others, but in this case, following this logic, SN1 may be your choice. Definitely not SN2 because it's a tertiary. Tertiary position, SN2 never happens. Secondary maybe, primary strong. Tertiary never SN2. SN2 inverted. Now here the question is, nucleophile can act as a base. You need to choose. If the nucleophile is a hard nucleophile, like lithium or magnesium are the chloride, Grignard reagent, they are hard reagent. They react faster with the water. That means they behave as base. To make a nucleophile, more prefer the carbon. We need to make it softer. To do that, exchange those hard metal. Hard metal means closed shell metal with transition metal with open d electrons. So that's not perfectly closed, it's a little softer. So this reagent, if you combine this together, it forms better nucleophile to attack carbon. Do you remember the name of this reagent? Suzuki, good try, but that is here, not with this combination, palladium with the boronic acid, the aryl halide reaction is Suzuki, that's here, different reagent here. This is a Grignard reagent. Actinium mixed together with copper metal exchange to make it softer.
Reduction.
It's not reduction, it's just exchange of the metal. Okay, so based on this, we move to okay, today we are going to study about elimination reactions. So this was the last page we studied last time. Nucleophile base, it can be same identity. If that electron-rich motif attack here from behind, push this out, SN2 reaction. If that nucleophile attack here, all of a sudden it acts as a base because it took proton. And push on the same direction. Then it's E2 reaction. So those mechanisms now you can see here. This is secondary antitralite. So secondary means it can be either SN1 or SN2, or E1 or E2. Now here, if this is utilizing this reagent, now if you look at OH minus, what do you feel? OH minus, electron poor or electron rich?
Each.
Electron rich. Is it nucleophile or base? it may be both, but OH minus is typical base. Right? That's kind of a hard structure. Now, it can act as a nucleophile, but at the same time, it can be base too. Hydroxide similar. Alcohol with H is removed. That's alkoxide. You can see ethanol and ethoxide by removing those protons with base. Alkoxide, OH minus, hydroxide, they are kind of a hard nucleophile. Means they can act as base. So if you have a choice, if it attack, still, if it attack here and replace this, then SN2 reaction. But the product seems like it's not SN2 product, elimination product. Then we should think again. What happens? So here, the proton attack is not on this carbon, that's carbon next to it. This is bromide side, carbon to the next, this proton. Okay, attack and push out and push out. So then, two options. Carbon here, this carbon or this carbon. Base attack here, push down and push out. Or attack here, push down and push out. Now the result. What conclusion can you make by looking at this ratio? Which one is more preferred? More substrate alkene is more stable. We have learned it before. Right? By what mechanism? Say again? No, what? Markov-Nikov is when addition happened, the more substrate position is preferred. That's Markov-Nikov. This one? Hyperconjugation. By hyperconjugation, more substrate position is more preferred. Okay? So if there is an option of a double bond forming, this is terminal. So HHH, 3H, 1 atom. Here, 2 atom. More substrate position is more preferred. Okay? Similar way, now here, attack chance. Maybe attack here, making this, versus attack here and making this. Okay? This is more preferred. Now this one is a little less because the number of attacking site is 6. This is only 3. That's why it's a little more, but general trend. Which one is major? More substrate. Now this is elimination product. Elimination mechanism, 3 mechanisms possible. First of all, E1 mechanism. Similar to SN1, it loses halide first, and it forms a carbocation. Once it forms a carbocation, 2 options. Nucleophile attack here, then SN1 reaction. Or nucleophile behaves as base, they take up this proton, then elimination product. Carbocation has 2 ways to go. Carbocation forming, if it's water, it's best by acidic treatment. If it's acidic treatment, then there's no base. That's definitely that's SN1. But now here, it is the base. And then if carbocation is formed, then carbocation is formed and weak base attack, and elimination is also possible. They are competing. Another possibility may be conceptually easier, E2. E2 is very similar to SN2. Just the attack position is different. Not carbon, it attacks hydrogen and push. Happens at the same time. That's why kinetically it's a second order reaction. Both of them, this one and this one, both of them are important. E2, they have a transient state or intermediate. Transient state, same as SN2. Now, very interesting, there's another mechanism. E1CD. Exceptional case. Base attack here, and then anion is formed. If the anion can be stabilized by other motif, we will see that example later. Then chloride leaves layer by pushing this down and then push it down. Very exceptional case. Sometimes we see this kind of mechanism too. But basically, all of them are elimination product, elimination reaction. E1, carbocation, compete with SN1. E2, similar to SN2, and strong base would be preferred. Strong base is a strong nucleophile usually, just the different the attack position. Strong base prefers E2. Okay, now here. I can highlight OH minus. SM2 possible. SM2 possible. SM2 is not possible because it's a tertiary position. Tertiary 2 steric. So even though OH minus want to attack, cannot attack this position, too crowded. Then only option is attack either here and push down and leave out. So double bond here or double bond here. Attack here, this proton, attack, push, push. Which do you think more preferred product? A or B? Because A is more substitute, you think? This is A, this is B. A is more substitute? No, right? B has a 1, 2, 3. A has only 2. Terminal is not preferred. More substitute alkene is preferred. This reaction, E2 reaction. Strong base rather than stabilizing carbocation. That prefers E2. So E2 reaction, conceptually, maybe it's easy. Base attack, down, down, very similar to SM2. Not attack here, attack here. Okay. That direction is also very important. So to check whether that's E1 or E2, product looks like a similar, but if you wanted to determine whether this is really through E2 reaction, SM2 reaction, we could get the result by inversion or retention or rationalization. If it's rationalization, that's SM1. If it's inverted, that's SM2. E1 and E2, we can try to make here, change this hydrogen with the deuterium. Deuterium is the atomic weight 2 isotope of hydrogen. Then chemistry, base should attack here and then push it down, and this bromide will push it out. Then the first step reaction is cleavage of deuterium or hydrogen. Base attack this. If it's heavier, reaction is slow. So when proton is here and hydrogen is here, hydrogen reaction is faster. And if you change it to the deuterium, if it becomes slower, that proves that this reaction is E2 reaction. If it was E1, the cleavage, first the cleavage is here. Bromide is removed, and then carbocation formed. Then the next step, it doesn't matter, right? Reaction rate is determined by the first intermediate forming. Then cleavage of this is not important. Whether it is slow or fast, it doesn't matter. If it is a E1 mechanism, you don't see this isotope effect. This is what we call isotope effect. If you change isotope, and if a heavy isotope is making the reaction slower, that means that breaking part is reaction deterministic. Okay. Rate deterministic. In SM2 reaction, attacking to the carbon and then release this, that should happen at the same time. That's rate deterministic. E2 reaction, come here and break this bond and then break this bond. Should happen at the same time. That's why this is rate deterministic, only one step of differential state. So this is the evidence experiment. We can prove whether this is the E2 reaction or not. Now, if there's a two conformations, this conformation, anti-conformation, base come here and attack, push down, looks like it's a similar attack here and a little shifted but same direction, push it down, then this reaction happens. E2 reaction. If this is overlapped like this, even though it looks like it's on the same line, now electron flow is base come here, electron push it down, somehow it should come back and attack this way. It's not really favored. This reaction is not favored. E2 reaction happens when it has this kind of anti-orientation. Makes sense, right? The electron flow should be on the same line. So can we explain that? So proton is here, base is coming here, and smoothly moving like this. Then this double bond form E2. Nucleophile SN2 reactions, electron comes from behind and pushes this out. It should happen at the same time. E2 very similar, but attack here, not the carbon. Attack here and push down. Okay. On the same direction, it works better. Now again, if this is attack here and push it down, similar way, same, one more time to show, come here and then same time. If it is rotational bond, then you may need to choose, but now if it is case of a cyclohexane ring, now we know some of those structures can be fixed. So in cyclohexane, it's a chair conformation is most stable, and two positions. One is the axial position, and one is the equatorial positions. Two possibilities there. Now, if it is axial, now this looks like same direction. If it is axial, this looks like anti-directions. Okay, base come in and push it down, and this direction happens. If it's Bosch, and this is equatorial, then this one should react with this trans hydrogen. It cannot react with cis hydrogen. Right? It should be trans direction. If it's axial, then it can happen. But if it's equatorial, it's difficult because of this direction. That's why now this chair conformations is flexible. Right? One time like this, and then the other time can be changed like this. So you can change those conformations to chair. But we can anchor the structure by putting a big group on one side. The biggest one is a T-butyl group. This is a little smaller than the isopropyl. The T-butyl, once it is localized in one position of equatorial, then 99% will fix on this conformation. Now with this isopropyl, maybe a little better, but still, this is the preferred structure. Now, HCl is most of them are axial. If you add a strong base, then base attack here, push, and generate this double bond form in comparison. Now, with this structure, and then chloride is down here, and this is equatorial. This is down, so this double bond cannot form. Then, only chance is trans hydrogen and chloride this side, and this should form, but this is this kind of orientation, not this kind of orientation. That's why this reaction does not happen. This product cannot be happening. But this is not perfectly locking both the structure. Small amount of configuration can be changed like this temporarily, maybe 1% out of total. And then with this form, now attack here, and it can form this product. And it goes back to this. So very small population. If you add here T-butyl, it may not go this way. It's too strong. It cannot have a chance to come here. If it is isopropyl, small population can go this configuration, different chair conformation. Then this reaction happens. After reaction is finished, it goes up. Now product position is different. Here, double bond formed here. Here, double bond formed here. A little complicated. you may need to look at several times. Okay, based on this, so this is E2 reaction. E2 should happen on the same direction but opposite direction can happen. Now E1 reaction, what do you need to have E1? What intermediate do you need to have? Carbocation intermediate should be formed, similar to SN1. So in SN1, we have seen this kind of cases. Tertiary is preferred because the tertiary carbocation is stabilized. Alkyl halide or tertiary alcohol with the acid, both of them can form carbocation intermediate. Once it is formed, the two options. Tertiary carbocation with water, and either water can be attached to that or eliminate. It's a continuum reaction. Depending on the conditions, it's difficult to even to predict the relative amount. Carbocation can generate two products. Previously we thought about only SN1, but now we needed to think E1 options. Carbocation is a cation, proton is removed, then this one. Or nucleophile is coming and attached, then SN1. In this case, this is a planar structure. Nucleophile can come from the top, from the bottom, no difference. Racemization. This the starting material was the type. Now you have this. Now this is isopropyl again. If they can change to each other. If you use E2 conditions, this is not preferred one. This is more preferred conformation. So we have seen it can form small amount of this. Now it has axial with a strong base. Strong base prefers E2 reaction. Attack here, push this down, and then form this product. If it's a strong base, then E2 is preferred. This is 100% conform. Now, in this case, this is not tertiary position, but with mild base and polar environment, like the water condition. Then this chloride is removed first. Then carbocation formed here, secondary carbocation. Then option of reaction and the removal of the hydrogen can happen from this or from this. Now product is same product with this, some amount happens, but the other side, this product is there. This is preferred because this is more serviceable. If you can understand these two, then you want to you fully understood. Summarize. E2 reaction is preferred by strong base. E1 reaction is preferred by polar solvent. Sometimes it's mixed conditions, but if you want to push to one reaction, E2 strong base, E1 carbocation stabilization. That's what you do. Now, last the mechanism of E1CD. So usually E1 case, chloride was removed first and carbocation is formed. Or base attack here and then push, two-step reaction happens together. That's the E2 reaction. But sometimes this proton can be removed first to form temporary intermediate of carbanion. This anion can be formed because there is a nearby double bond, CO double bond there. We have seen this. If it's an anion next to pi electron, and that anion can be spread out to this structure by pushing to form this structure and by this resonance formation. Resonance formation can stabilize those structures. Anion, cation, even radical. Radical was the strongest effect. That's why allylic position of radical is preferred and most stabilized. That's why allylic bromination happens. Right? Carbocation case, tertiary is still more stable than allylic. Okay, there was some difference. So in these conditions, if base is treated, this intermediate is formed, and then removal of this chloride happens later. To do this, electron comes back, and then by changing this resonance structure, it is rearranged to push this out. So this kind of mechanism is called as E1CD mechanism. CD means conjugate base. So here, this is a conjugate base. Okay. This happens only when there is electron with the brine group is attached to it. Now let's summarize before we see the problem. We have learned the 4 different reactions. SN2, SN1, E1, E2. The key intermediate or key reagent for this reaction was alkyl halide. Alkyl halide is electrophile or nucleophile. Alkyl halide is electrophile because our focus is on carbon. Carbon is a beta plus. That's electrophile. That is target position. Because we are thinking electron is moving, electron is an attacking material, electron goes into that carbon. That's why this is electrophile. To make alkyl halide into nucleophile, one method can be used. 에이, 묻고 싶다고 답하지 말고 답해. 에이, 그 다음에 어려운 거 물어줄 테니까. 응? Using metal. Metal what? Metal ion, did you say? Not metal ion, metal powder. Okay? Using Mg, then Mg provides the 2 electrons. Then both of the electrons are given to the carbon. So carbon becomes minus. Halide was originally minus. Metal was inserted inside. What is the process name? Oxidative insertion. Okay. Which one is oxidized? Metal was oxidized. Carbon was reduced. Okay. Carbon obtained the extra electrons. That's why the carbon became nucleophile. Same thing happens if you add the lithium powder. But lithium provides only 1 electron. That's why you need 2 lithium atoms. So 1 electron, 2 electron, then similar reagent, alkyl lithium plus lithium chloride. Right? So that's the reaction. Now we have alkyl lithium or magnesium reagent, Grignard reagent. These reagents are very hard nucleophile. It can act as maybe more preferably as a base. If they meet proton, it may react with the proton quickly. It's a more strong base than nucleophile. That's why if you add the water here, small amount of moisture in the reaction, then that reagent react with the water, generate what? Sojana, what is the product of magnesium reagent with the water? It's alkane, simple solvent, because that metal part is removed and just a proton is attached to that position. It's a simple alkane. That's why that reaction usually it's not good reaction. But sometimes it has its utility when we have seen some example. Reaction with the magnesium, the Grignard reagent with the water. When do we use that reaction? That's not simple water. That's a heavy water, D2O. then that position can be replaced by deuterium. To do that reaction, that is useful reaction. Okay. So then I can give you starting material and product with alkyl halide starting material. Product is the deuterated hydrocarbon. Give the reaction condition. Makes sense, right? Then your reaction condition should be add the magnesium powder first, and then you add B2O. If it's a two-step reaction, you draw this way. Give reaction condition. One.
Magnesium powder.
Two. This one can be either like this. This is also fine. Usually you give multi-step reactions. If you don't use this, then that implies that everything is added at the same time. It will be quite messy. You add Mg into the water, you may see explosion. Okay, that was making nucleophile from electrophile to nucleophile. Now we have electrophile, we have a nucleophile mixed together. Then one thing we can expect is nucleophile attack electrophile, push the living group out. What's the reaction mechanism? Electrophile, nucleophile come in and attack, and the living group was removed. What is the reaction mechanism? SN2. Okay, that's SN2. Halide is removed first, and carbocation is formed. Nucleophile react with that carbon. What's the reaction mechanism? That's SN1. Carbocation is formed. Proton is removed. Double bond is formed. E1 reaction. Electrophile, but nucleophile did not attack directly on carbon. It attacked hydrogen side, proton side, and then push and form the double bond. E2. Okay, that's what we have learned so far. To get E1 or SN1, you need to have polar solvent to stabilize carbocation. To get SN2 reaction fast, you avoid protic solvent because not to stabilize the nucleophile too much. Okay. To push the reaction to E2 reaction, you may use strong base because E1 reaction, it doesn't matter whether it's a strong base or not. Water is enough because carbocation is so reactive, even very weak nucleophile still can finish up the reaction. Okay. Those are the summary of these four very basic but very fundamental organic reactions. Okay, let's look at the example. The question: what product do you expect? Alkyl halide looks like some nucleophile or base. Looks like a strong base. Alkoxide is like OH minus. It's like a strong base. Maybe two possibilities. This can attack maybe here and then push this out. Then SN2. But this is very hard and looks like strong base. The product, that's the main product, is the E2 product. Attack this proton here and then push. Okay. How about this? Now acid and water. Even though that's not tertiary, acid means there's no good nucleophile there. Or maybe weak nucleophile there. This is deprotonated, then HCOO minus. We have seen acetate was a nucleophile. But under acidic condition, there is a weak nucleophile. Under base condition, it can be reasonably good nucleophile because it can be minus, but no, this is acidic form. So this should attack with this lone pair electron. Then, what do you think? Water. SN2 reaction? May not. E2? May not, because it's not strong base. And the question is, with this, you may have a mixture of the two. That means what is the intermediate? Carbocation is the intermediate. Once carbocation is involved, it's difficult to control those reactions. Carbocation was found here, cation, and then this one, weak nucleophile come back and then finish up the reaction. Or the proton here that was removed to form this. This is a terminal alkene, but there is no other options. There is no other more substituted alkene can be formed. So this is the only product. Okay. Okay. This reaction, when we started this chapter, this was suggested and observed a long time ago. So let's review this reaction again. Originally, this was alcohol. And then PCl5 or PCl3 reaction. And then alcohol was exchanged with the chloride. What do you think? This reaction is mechanism? SN2. Inversion happens. Right? Alcohol attack here first, and the still minus come back and attack. So one inversion happened. And then from here to here. Silver oxide is like the base. And then this is like in situ generate OH minus. If OH minus attack here and then form this, that should be SN2 reaction. Right? But it is a retention. From here to go here, that's another inversion. But again here, this is a retention. So in the beginning, that was not clearly understood. What happened is here. When chloride is formed, before that react with this OH minus, this internal carboxylate that attack here first. And then it forms this kind of cyclic intermediate. If this happens, this reaction mechanism here, this is also attack here, push this out. This is also SN2 reaction. One SN2 already happened. One inversion already happened. And then OH minus come in and then push here and push this out. Another inversion happened. Two inversions happened together. That's why total result is from here to here retention. Okay. Internally, this was attacked, and then inversion happened first. Intermediate is formed, and then OH minus attack here and push this out. That's why two inversion make total retention. Okay, so for this type, we have learned two cases. Tosyl chloride is one case. If alcohol attack tosyl chloride, nothing happens, retention. Alcohol with PCl5, one step inversion happens. If you use a nucleophile again, then another inversion happens, comes back to the original retention product. Okay. So that's summarized here. In these reactions, I promise you, I will show you this question in the final exam. Why this is retention? Okay. Then this part, not in your textbook, but you will see this in your notebook. I will put it up. Let's start with this. Okay, we are up to here. All the organic chemistry is done up to here. Now we are going to the analysis technique, mass spectrometry, and IR, and NMR, and 1 week of review of the session, then we finish. Any question we learned so far for the organic chemistry reaction structure part? Okay, up to here you learned not too many, but a little confusing several terms. Those parts you need to practice with the different reactions. Okay. Then you can get this general trend when you can get one type of reaction. So most likely you will see this type of problem. Then you need to decide. I have 4 options. Then which direction the reaction may go the best. Or if there's any product is given like this, then what mechanism is applied to this? Okay. So the final exam, most likely you have reagent, conditions, and show the product. Or reactant, product, give those reaction conditions. Or you have one step of the reaction or 2 step of reaction, explain the mechanism. Okay? So that type of problems are the practice. That will be a good basis for moving to organic